you, Noah, and very happy to be here today to share an update on behalf of the Artemis 3 geology team in terms of all of the hard work that is going on to plan for the geology investigation on Artemis 3. Next slide, please. So just a reminder about what the role of the Artemis 3 geology team is, and by corollary, what it is not. Our job is to participate in defining the lunar science objectives for the Artemis 3 mission, designing the surface campaign to satisfy those objectives, supporting real-time mission operations from the SUR and the SMOR, as you heard about from Kelsey this morning, performing the preliminary examination of returned lunar samples, and synthesizing initial science results from the mission. And one of the key words here is participate. We are working together with a really great team across NASA, including the internal science team, and then a lot of the just broader Artemis team that is working really hard to make sure that the science investigation on Artemis 3 is as amazing as it can be. I will just give a brief update today related to, what our job is and what we've been working on. We have finalized, that should probably be in, air quotes there, as final as these things can be, our science traceability matrix, and we are working on a publication to get that out there to the community. So you can see the details of that. That also traces then to the sampling plan. And we were also asked to do an analysis of sample mass, so I'll share some of that work. We have been doing an assessment of the candidate landing sites. I heard about the candidate regions from Tamara. We've been looking at sites within those regions in terms of their suitability for meeting the geology objectives. So I have a brief update there, and then some of the testing and training that is going on with mission simulations. We'll touch on that. And then Matthew will have much more in the next talk. Next slide, please. So our science traceability matrix is grounded in 4 geology goals. These come from the Origins World's Life Decadal Survey. These are also the Moon to Mars objectives for lunar and planetary science, looking at understanding the origin of the early evolution of the moon, the record of inner solar system bombardment, how the environment controls regolith properties, and then a goal focused on volatiles. Each of these also then includes 3 objectives. So we have 12 objectives across the full STM. Next slide, please. I wanted to give you just a brief look at what the STM looks like, and apologies for this tiny font, so I'll just try to describe what's in these boxes really quickly. This is an example of one of the objectives here, our objective A1 in the early evolution of the moon goal is looking at magma ocean models for the timing and processes that led to the formation of the crust. We've prioritized each of the science objectives, or really ranked them in an effort to help communicate the priorities to all involved, and especially ultimately the crew, so that they understand where these things rank and how the work that they are doing feeds into those, so they can make autonomous decisions as needed. We have hypotheses here, and then the observables needed to close those. Things like looking at the ages and mineral and bulk chemical and isotopic compositions of materials in the south circumpolar region in comparison to those in the Apollo zone. And then the part that we've added a lot of detail here is looking at the required sample or investigation locations. So this is done in a site agnostic manner. So these are at kind of typical sites. Where would you want to sample? For this one, that would be, for example, like near rocks that have been excavated by a large impact crater that has excavated through the more mixed regolith. And then the types of samples that you would want to collect there. Here in particular, it would be, boulder chip, rock, hand sample sized samples and regolith rake samples. Other areas selected for diversity across a site, and then we have a number of types of samples that are just location agnostic in terms of if you find a specific type of sample. That is always a high priority. When you add this all up across all of the 12 objectives, there's a lot of overlap where different kinds of samples and investigations will help support multiple objectives. But this gives you a site agnostic investigation plan. And we are using this investigation plan as a starting place for planning at specific sites within the candidate landing regions. We've had an opportunity to look at multiple of these now, and we're currently in the process of looking at 3 additional sites for an upcoming sim. When you kind of track how that all adds up, our current estimate at a representative site is that this yields about 10 science stations, 35 to 40 unique sample types, and about 6 hours of task time at the stations. And that is exclusive of traverse time to fulfill the STM objectives. So this is what we think we need to fully satisfy our geology investigation plan. It's important to note that the actual EVA utilization time that is planned for this investigation is still being evaluated, and there are many different factors that will contribute to the ultimate time devoted to that investigation. Next slide, please. So in terms of the mass analysis, I'm just going to go through quickly an example here for Goal A. Goal A are looking at the early evolution of the moon. This one requires crystalline igneous rocks and diverse rock types from the lunar, the upper and lower crust, and then hopefully the lunar mantle, looking at kind of the masses of specific key rocks from Apollo and lunar meteorites that have been used to address this. Next slide. When you look at then the types of investigations and analyses that will be needed, you can get example masses that are required for things like the radiogenic isotopes, or for moderately volatile isotopes and the highly acidophile elements. And these are, in the kind of milligram range to gram. When you add them together, you want to do coordinated analyses on a single sample. That gets you up into kind of minimum sizes for some of these in, translate to about a centimeter size rock here. Next slide, please. Of course, we cannot count on being able to find all of these and pick them out neatly from the regolith or from clasts. These key samples are expected to be fairly rare across the landing site, especially the kinds of pristine samples needed. These require then starting from much larger sample masses. An example of what that looks like is, Apollo 17, where this polymorphic breccia originated from this larger boulder. And when you break that down into the smaller clasts, those are the kinds of sizes of materials that we're talking about. But you're starting from a sample that was over 3 kilograms. Next slide, please. When you take the kind of holistic look across the different types of samples that we are going to need to meet our science goals, these are the kind of float or the hand sample and chip samples from boulders, rake samples, scoop and trench samples, and drive tube samples. Next slide, please. Each of these has really important pros as well as some cons for meeting the different science goals. Things like, rake samples are really great for characterizing the diversity of the site. Drive tube samples are just absolutely required if we're going to look at volatile samples. These come with, in some cases, negatives. Drive tube samples also take the most time to collect. They have much more massive containers. But building across all of these, if you go to the next slide, that means that we are going to want to endeavor to do all of these from the kinds of locations specified in our science traceability matrix that best capture the variety of the site. Next step, please, there. And when we go through all of the objectives in the SDM, this gives us a kind of look at our minimum sample set here across the different sample types. Adding those all up, you get to just under 40 kilograms. Next slide. And that is excluding the sample containers. So some of this is coming from a question of, you know, a robotic mission can make a lot of progress with a sample mass of 100 grams. Why do you need so much mass? And so I think that the nature is really in the types of science questions that we are asking. For goal A, we are looking for pristine end members that should be expected to be rare at some of these sites. For goal B, that's the impact bombardment. We really need to develop a sample set that gives us really good statistics for a very complicated chronology picture. And then for goals C and D, looking at the regolith and volatiles, diversity and sampling across the diversity of environments is really key for those. So all of these are really driving the desire for mass. And we think that the kind of masses that we're looking for here fit neatly, even once including the container masses within the allocation here. You've probably heard the kind of 100 kilogram return mass for Artemis. So we think that the sample masses are for Orion. So the sample masses are going to meet the geology objectives here. Next slide, please. That was a great overview from Tamara about the landing sites and the candidate landing regions. I wanted to just add in our geology team perspective of a science evaluation of landing sites within these candidate landing regions. Next slide. Thank you. So we were tasked by Tamara and her team with evaluating the scientific potential of landing sites for meeting our defined goals and objectives. And timely to the discussion this morning about science figures of merit, that is what we did. We developed figures of merit to rapidly evaluate these exploration areas. The exploration area being, the kind of extent to be explored surrounding a single landing site. And we also did, just a qualitative geologic assessment, and these compared favorably. When we looked at our goals and objectives, as well as what was really kind of discriminating between the types of sites within the candidate regions available, that led us to kind of desired targets. These include rocks excavated from distinct specific craters that help get at stratigraphy, and also more potentially kind of less mixed material, I'll say, as well as diversity of environments and access to permanently shadowed regions that have the potential to host water ice near the surface. We combine those together across, adding in constraints related to slope and PSR size, et cetera, to get a science figure of merit. These are actually old numbers on here. When we first looked at this for a previous set of sites, around 30% of the sites were especially promising for meeting our science objectives, and 40% were, distinctly less favorable. This was really clearly showing that the specific landing site is going to have a very large impact on how well we can address the geology goals. When we looked at this again for the 9 candidate regions and specific sites in there, the numbers are substantially more favorable. And so that is great to see that the science evaluation helped kind of improve the chances here of selecting a good site. And we're glad to be able to provide input here. There are more details in an abstract from Caleb Bassett from LPSC. Next slide, which is very, oh, that was backwards. We're going backwards. Very briefly, because Matthew will cover this much more, but as we are applying our science traceability matrix to mission simulations that are using the actual lunar data, because we're doing some of these in VR, we're able to test out our STM, improve and streamline our sampling plan. Some things don't translate to VR, so we're still doing field exercises to understand, working with the camera and working with the geology sampling tools. Next slide, I will end on just a note that our motivating goal, as Noah said too, throughout all of this work, is to really maximize the science of the mission and to collect a set of samples and data that will serve the community for decades to come. We really continue to value community input on these plans. Thank you to those of you who have provided input in the past. You can always reach out. We love to hear it. And we are really looking forward to participating scientists joining the team as soon as that call is out there. So thank you.